Hi, I'm Mark Bryce-Seaman. In this video, I'll be discussing applying the methods of direct proof to prove the contrapositive of universal conditional statements, and I'll also be talking about a new form of proof, a new style called indirect proof, the method of proof by contradiction. I want to start by noting that section 4.7 is the first section of chapter 4 that has a title that does not start with the words direct proof. Sections 1 through 6 all have direct proof and counterexample in their title. We didn't cover section 4.6. Sections 4.7 and 4.8 have the words indirect argument in their title. There are two things that we can infer from that. First of all, the fact that indirect proofs, whatever they are not presented in the book until after 6 book sections about direct proofs. That tells us that indirect proofs, whatever they are, must be harder or more confusing than direct proofs. And also from the fact that there are 6 book sections about direct proofs and only 2 sections about indirect proofs, that tells us that indirect proofs, whatever they are, must not be needed as often as direct proofs. This should say direct proofs. Now, I'll also add that I've found that students often use indirect proofs in situations where an indirect proof is not appropriate. And the results are always confusing and they're incorrect proofs. One of my colleagues has an opinion about why this happens. He thinks that students are often confused about the mathematical statements they're being asked to prove, and students are also often confused about how indirect proofs work. And he thinks that perhaps students think that maybe the proof structure that they don't understand must be the proof structure that's needed to prove some statement that they don't understand. That if they're confused about both those things, maybe they go together. It doesn't help that in math books, indirect proofs are often used in places where a direct proof would be simpler and clearer. That makes these proofs much harder to read. Even in our book, which is very well written, I find that indirect proofs are overused. And for instance, I feel that many of the section 4.7 examples that use indirect proofs and in the exercises that ask the students to use indirect proofs, those examples and exercises can be more simply done, more clearly done with direct proofs. That means that the student reading our book might get the wrong idea about how often indirect proofs are actually needed. In this video, I'll focus on 2 things: teaching you methods of indirect proof, and also pointing out situations where indirect proofs are used or suggested, but direct proofs would be better. Both of these things will make you a better writer of proofs, and they'll also help you be a better and more critical reader of proofs. I'll begin by doing some examples where the proof methods that we already know will work just fine. This serves 2 purposes. It'll give us a chance to review our current proof methods, and then later we'll revisit these examples and write indirect proofs, and we'll see how much more confusing and how unnecessary the indirect proof structure is in situations like that where a direct proof is possible. So let's review the method of generalizing from a generic particular element. Remember that it's used to prove a universal statement for all x in the domain Q of x, and the structure is this. You start by saying, suppose that x is in the domain, a generic particular element, and then you have a bunch of steps, and you end with, therefore Q of x. So whatever the predicate is shows up as the very last statement. Whatever the domain is shows up in the statement of the first statement of the proof. Here's our first example then. Prove that there is no least positive rational number. It's book problem 4.7, number 7. In the book, they tell the student to prove this using the method of contradiction. I'm doing this as our first example because we haven't learned the method of contradiction, and the method of contradiction is not the best method to use to prove this statement. So I want to use this as our first example to show how our existing proof methods are good in a lot of cases where it's common for people to use more difficult proof methods. So we're going to prove this using our existing proof methods. First thing we need to do is rewrite the statement in a form that will make it clearer how to build the proof. So let's give our statement a name. Let's rewrite it in a different form and then write it formally. So our statement is going to be called S. So I've rewritten the statement a little bit. I've put these words in front. It is not true that there exists a least positive rational number. That will make it easier to rewrite the statement formally. So the way I've written it is completely equivalent to the given sentence that we're supposed to prove. But this presentation makes it clearer to write it formally. So our words, it is not true that, they get translated into this negation symbol. And then the statement, there does exist a least positive rational number, gets translated this way. It would mean that there exists some positive rational number R such that for all positive rational numbers Q, R is less than or equal to Q. So the green statement here is the statement that there is a least positive rational number. We park the negation in front of it, and we now have there the formal statement that there does not exist a least positive rational number. Now that's the thing that we're supposed to prove. It turns out that it's a little bit easier to structure a proof if we rewrite this so the negation is moved to the right. We've had this come up before in the course. Here's a case where it really makes a difference. So I'm going to move the quantifier to the right. When I move the quantifier past that first existential statement, it switches to a universal statement. Now let's move the negation one more notch to the right. When we move the negation past this quantifier, it turns that into an existential quantifier. So finally we have the negation parked in front of this little predicate. So now let's rewrite this one last time using this negation on that predicate. The negation of R less than or equal to Q is Q less than R. So we'll rewrite this formal statement one last time with that in the final place. So the statement that we need to prove is this. For all positive rational numbers R, there exists a positive rational number Q such that Q is less than R. That's what we need to prove. Now, that's a universal statement, so we'll use the form of generalizing from generic particular element to prove this. We'll do that on the next page. So there's our statement recopied here. That's our statement S, and we're going to prove this using the method of generalizing from generic particular element. So we have no choice about how this is going to start. We've got to start with introducing such an R. And we know how this has to end. It's got to end with the predicate. So there's our frame of our proof using the method of generalizing from a generic particular element. Now notice there's some more stuff that we have no choice about. That's a defined term to say that R is a positive rational number. So we have no choice about how we have to go from here. We have to unpack that definition. Now, we need to end with this. We need to end with a rational number Q that satisfies this. Now here, I think it will be clear enough if I just dive in and fill this gap. Because we've got a rational number R that's positive, And we need a rational number q that's a positive rational number that's less than r. And this is a gap that's small enough to jump. So I'm going to just introduce that as my q. Notice what that is 1/2 r. Notice two things about that furthermore. That number q is going to be rational because it's a ratio of two integers and the integer in the denominator is not 0. Furthermore, q is positive. And furthermore, q is less than r because it's 1/2 r and r is a positive number. So we've bridged that gap. This blue statement is actually statement 4. The justification for statement 4 is simply by statement 3. So see, this is a very short proof. It really depended on what we did on the previous page, realizing that there is a smarter way of writing the original statement into a form that made the proof structure obvious. Okay, let's go on. Now I want to review divisibility and the quotient remainder theorem. So remember we had statements like this in the section when we were talking about divisibility. To say that n is divisible by 3 means this. There exists an integer q such that n equals 3q. Now recall the quotient remainder theorem. That theorem. Given any integer n and a positive integer d, there exist unique integers q and r such that this equation is true and this inequality is true. In the previous video, we discussed this question. Suppose that n is some integer, and suppose you choose a value for d. So we don't know what n is, it's unknown, but we've got some chosen value of d. What does the quotient remainder theorem tell us about n in that case if we know that d is 3? Well, in the previous video we discussed that the quotient remainder theorem becomes a great big OR statement. It says either this is true, or this is true, or this is true. Exactly one of those. This is the exclusive OR. So in other words, the quotient remainder theorem tells us that if you write an equation of that form with your unknown green n and your value of 3 playing the role of d, and if it's in the special quotient remainder theorem form, that is, if the remainder is greater than or equal to 0 and less than 3, well, that means that the remainder has to be either 0 or 1 or 2. Those are the only possibilities. So now compare the statement involving divisibility and the statement from the quotient remainder theorem. We see that this statement, to say that n is divisible by 3, means the same thing as this. If you have this equation and it's in special quotient remainder theorem form, that is, if the remainder is in that inequality, then the only possibility is that the remainder has to be 0. So to say that n is divisible by 3 means that when you write one of these equations in the special form that obeys this inequality, then the remainder is the number 0. Our second example is this one. Prove that for every integer n, 3n plus 2 is not divisible by 3. Now this example is actually an exercise in the book, section 4.7, number 4. In the book, they ask the reader to prove this using the method of contradiction. We haven't learned the method of contradiction yet, and I feel very strongly that the method of contradiction is unnecessary to prove this statement. So that's why I've put this example here as example number 2. I want to show how this statement can be proven very simply without the method of contradiction. This is a universal statement. There's the formal version of the same statement. And so let's prove this. Let's use the proof structure of generalizing from a generic particular element. We have no choice about how this proof will begin and how it will end. There's how the proof has to begin, and here's how it must end. So how do we bridge this gap? Well, it will help if we introduce a name for this quantity, 3n plus 2. I'm going to do this in a color-coded way. So I've just introduced the letter M, and I've also colored it green, and I've colored that 3 blue, and I've colored that 2 red. Now notice about this equation here. It's in that special form, the quotient remainder form. If we think of that red number 2 as the remainder, it satisfies that inequality that's got to be satisfied. So this equation is of the form m equals dq plus r, where d is the number 3 and r is the number 2, and it satisfies the requirement that 0 is less than or equal to r, which is less than d. So this is what I called in my previous video QRT form, quotient remainder theorem form. Now think back to what I mentioned on the previous page. To say that some number is divisible by 3 means that if you put that equation in that special form, the remainder is 0. If the remainder is not 0, then your number is not divisible by 3. And so our last statement of the proof that we knew had to be there is our statement 3. So there really is nothing to this proof. To prove that this is true for every integer n, 3n plus 2 is not divisible by 3, merely requires that you pay attention to the thing that we're looking at and realize that it's of a form that is telling us our answer. There's nothing to do here except realize this thing that we realized before, that the idea of divisibility is related to the idea of what's the remainder when you use the quotient remainder theorem. So as I said, in the book, this is an exercise where they ask you to use the method of proof by contradiction. We'll revisit this example later when we know that method, and you'll see that the method makes things worse. Now I want to review the method of direct proof. Remember that if you take that method we use of generalizing from a generic particular element and you use it to prove a universal conditional statement, the resulting structure is called the method of direct proof. So if you want to prove one of these things for all x in the domain, if p of x, then q of x, and you apply this method of generalizing from a generic particular element, you get this structure. And that's called the method of direct proof. Now I want to discuss the idea of proving the contrapositive. Recall that a conditional statement is logically equivalent to its contrapositive. So this statement, if p then q, is logically equivalent to this statement, if not q then not p. The same thing holds for universal conditional statements. They're logically equivalent to their contrapositives. So this statement, for all x in D, if p of x, then q of x, that's logically equivalent to this statement. For all x in D, if not q of x, then not p of x. Well, in many situations, it's possible to prove a universal conditional statement S very simply by just simply proving the contrapositive of S. Since the contrapositive of S is a universal conditional statement, the proof structure will be direct proof. So, for example, example 3 is prove this. For all integers n, if n squared is odd, then n is odd. This is actually a book exercise. Well, our job is to prove that. It turns out that it's very easy to prove the contrapositive. So we should write down the contrapositive of S. Contrapositive is for all n in the integers, if n is even, then n squared is even. So let's prove this with a direct proof. So the proof structure is clear. We have to start by saying so there you can see that in statement 1 we've introduced an element that has the qualifications that it is in the domain, and also that it has the qualification that's specified in the hypothesis. So that's the first line in a proof by direct proof. The last line of the proof is going to have to be this. All right, that's the frame that we have to use. Now notice there's other stuff that we have to use as well. There's a defined term in the first statement. So we have no choice as to what's going to have to go on in the second statement. We have to unpack that definition. Also look ahead to the very last statement. That statement contains a defined term, so we have no choice about what's going to have to come before that. So you see that because this last statement has that phrase in it, n squared is even, that statement has to be preceded by this statement. So that also means that the final statement of the proof is going to be justified by that preceding statement and the definition of even. So we use the definition of even twice in the proof. There, unpacking the statement from statement 1, writing it again in a less abbreviated form, and then we use the definition of even again in the final statement to pack up the definition. That is, we take these words, a lot of words there, and we rewrite them using the more abbreviated terminology of an even number. Okay, so there's our gap that we've got to bridge. We want to get to this equation. We don't know what j is, but look, we can get to work. We know what n is, so let's just build n squared and see where it takes us. So look where we have gotten to. We've gotten to n squared equals 4k squared. Well, we want to get to here. We want to say that n squared equals 2j. So let's rewrite what we've got in that form. Now it's very clear what we need to do next. We need to introduce something that can play the role of this j, and we know what it's got to be. So there's our j, and look, we're ready to wrap this up. Our black statement can be statement 5, and our blue statement can be statement 6. And that's the end of the proof. Let's do one more example. Let's prove this statement S. There's a typo here. This should say for all n in the integers. Well, we're going to prove this by proving the contrapositive as well. So let's write the contrapositive of S. So the original statement is for all integers n, if 5 does not divide n squared, then 5 does not divide n. The contrapositive is for all integers n, if 5 does divide n, then 5 also divides n squared. Let's prove this. We're going to use a direct proof. That's how the proof has to begin, and the way it's going to have to end is this. So that's the inevitable frame. Now let's think about what else is inevitable. Statement 1 has a defined expression in it. 5 divides n. So we have no choice but to follow that up with this statement. Also, look ahead to the end of the proof. The end of the proof has this statement, which is a defined term. So we have no choice but to precede that with the following statement. And when we have that statement there, we know what's going to have to be the justification for the final statement. So there's the gap that we've got to fill. We want to have an equation that says n squared equals 5j. Oh, look, well, we've got an n there we can use. We don't know what j is, but we know what n is. So let's just start building by building n squared. Now look where we need to go. We need to get to here. N squared has to be of the form 5j. So let's keep writing what we've got until we get to something in that form. So we need to introduce something that can play the role of j. We can see what it's got to be. It's got to be 5k squared. So we're ready to wrap this up. The black statement is statement 5. The blue statement is statement 6. So that's a proof of the contrapositive of S. And again, the book calls this kind of thing an indirect proof. I don't. The contrapositive of S means the same thing as statement S. So we just proved statement S with a direct proof. We happen to prove the contrapositive of S, but it's the same thing. Okay, let's go on. I want to review the idea of contradiction and contradictory statements. Remember that a statement form like this is a contradiction, because when any value of x is substituted in to create an actual statement, the resulting statement will be false. So for instance, if I substitute in the number 3 for x, then that becomes this statement, 3 equals 5 and 3 equals 7. That's false. If I substitute in the number 5 for x, then that blue circled statement form becomes this statement, 5 equals 5 and 5 equals 7. Well, that's false. So this is a statement form. It's not a statement, but whenever I substitute an x value in, it becomes a false statement every time. So that's why this is called a contradiction. Now, remember when I substituted in an actual number, like the number 3, that expression became a statement, a false statement. Well, there's a subtle thing here. I want to pretend now that x represents a particular actual number, like 3. Then that expression is a false statement. It's no longer a statement form. So the statement 3 equals 5 and 3 equals 7, that's an actual statement. There's no variable there. We say that that statement is a contradiction because the corresponding statement form is a contradiction. So there's a very subtle difference between the idea of a statement form and a statement. But the word contradiction can be applied to something that actually is a statement form or something that is a statement that has the form of a contradiction. Now, next I want to talk about the idea of contradictory statements. Suppose you have a list of statements like this. And statement 13 is this, the statement x equals 5. And farther down the list, there's a statement 17, which is the statement x equals 7. We say that those are contradictory statements. Now, of course, anytime you have a list of statements that has two contradictory statements on it, they can be used to form a contradiction. So this list of statements has two contradictory statements, these two. And I can use those to build this, because that list says all those statements are true. So the list says x equals 5 and x equals 7. So statements 13 and 17, those two statements are contradictory statements. The single statement 18 is a contradiction. So since it's always possible to form a contradiction once two contradictory statements have been written, it's customary to say that you've reached a contradiction even if the contradiction has not been written down officially. So if I've got this list of statements and I've got this statement 13 that says x equals 5, and I've got this statement 17 that says x equals 7, it's common to just say we've reached a contradiction. That is, statement 17 contradicts statement 13. Notice we didn't actually go the last mile. We didn't actually write down this form, x equals 5 and x equals 7. But you get the idea. If we wanted to, we could have squeezed in a sentence here that says x equals 5 and x equals 7. That's a contradiction. But we don't need to do that. The common usage is to, if you get to a point in a proof where you have contradictory statements, you just say we've reached a contradiction. But it's good to say clearly what the contradictory statements are. Now I want to discuss, finally, the method of proof by contradiction. We'll start by recalling the rules of inference from Chapter 2. These are valid argument forms. One of them was this one, called the Contradiction Rule. I'm going to write it a little bit bigger. Now, what is that actually saying? Remember, it was mentioned briefly in Chapter 2 that the letter C denotes a contradiction. In other words, a statement form that's always false. Or a statement that has the form of a contradiction. So this contradiction rule says, if P is false, then you reach a contradiction. Therefore, P must be true. That's a little bit weird to say. So I'd like to confirm that this really is a valid argument form. Remember how we do that. We use a truth table. So I want to use a truth table to verify that the contradiction rule really is a valid argument form. So there's a table that we can use. I'm going to add another column here. So the contradiction rule, remember, says this. So we need a column for the variable P, for sure. And we need a column for negation of P. And we need a column for C, sort of. You might wonder why I only have 2 rows if I have 2 variables. I should have 4 rows, shouldn't I? Well, no. Let's start with the rightmost letter. C represents a contradiction, so C is always false. Let's go back and populate the column for P and the column for not P. So there are the columns that we'll use to build this. So the value of if not P then C is true then false. Now remember how we use a truth table like this to consider the validity of an argument form. We have to indicate the columns that have the hypotheses. That's this column, just this one hypothesis. And we have to indicate the column that has the conclusion. And we have to find the critical rows, the rows where the hypotheses are all true. Well, that's only this one. And we have to look in that critical row and see what's up with the conclusion. In that row, the conclusion is true. We only have one critical row, and in that row, the conclusion is true. So therefore, this is a valid argument form. Let's go on. The contradiction rule can be used inside a proof that uses the method of generalizing from a generic particular element. The resulting structure is called the method of contradiction. So here's how it looks. We're going to prove a statement of this form for all x in the domain Q of x. We're going to prove it by contradiction. Well, we're going to start with the frame of the generalizing from a generic particular element. So we're going to start with, suppose that x is in D, and we're going to end with, therefore, Q of x. So there's our frame of the method of generalizing from a generic particular. But look, within that frame, we have this sequence of steps. Assume that Q is false, reach some contradiction, therefore Q is true. That's the same form as this. Suppose that P is false, show that you reach a contradiction, therefore P must be true. Or maybe say it a different way. If P is false, then you reach a contradiction, therefore P must be true. So let's look again at this. You see the blue outer frame of the method of generalizing from a generic particular, and then sitting inside of it is that black frame of the rule, the contradiction rule. The contradiction rule can also be used inside a proof that has the method of direct proof as its structure. So if we're going to prove a universal conditional statement for all x in D, if P of x, then Q of x, we would have the frame of direct proof. So suppose x is in D and P of x, and then sitting inside of that, we would have this structure. Assume Q is false. Show that you reach some contradiction, therefore Q of x is true, using the contradiction rule. Let me do an example. Example 5. This is an exercise from the book. Prove that the product of any irrational number and any non-zero rational number is irrational. So let me write this a little more formally. So that statement can be written semi-formally as, for all irrational numbers x and non-zero rational numbers r, the product of x and r is irrational. So let's do a proof by contradiction, but remember, that's going to mean that we're going to use the method of generalizing from generic particular element. So there's our first step, which is inevitable. And our conclusion is inevitable as well. Has to be that. X times r is irrational. So there's our frame of the proof by generalizing from the generic particular element, that blue frame. But within that frame, we're going to use the contradiction rule, and that will go like this. So statement 2 is we assume that xr is rational. In other words, we assume that this predicate is not true. And the justification is, well, we don't have to justify it, but it's worth saying again that it's an assumption. Now, what we need to do is we need to reach a contradiction. So how do we do that? Well, notice that we have two lines that have defined expressions in them. We have the first line that says r is rational, and we have the second line that says that xr is rational. So we have no choice about how we're going to have to proceed from here. In statement 3, we've used the fact that r is rational to say that r can be written as a ratio. Now, we know that the denominator cannot be 0 because that ratio has to represent a number. Also, we know that the numerator is not 0 because we're told that the number r is not 0. So we have no choice about that green statement. It's got to be there because that was there. Now we have no choice about what's going to happen next. We have to deal with this. We have to unpack that defined term. Okay, so we have no choice about the green statement. We have no choice about the red statement. Now look at this. We know that r is this. So let's get x by dividing xr by r. So x equals that ratio. Notice that the denominator is non-zero because neither b nor n is 0. Now we're running out of space here, so I need to move some of this down to the next page. So what I'm going to do is I'm going to move the blue statement down to the next page. All right, so look carefully at statement 5. It shows that x can be written as a ratio of integers where the denominator is not 0. Now look where we've gotten to. We have a statement that says that x is rational. But wait a second, go back up to the start of the proof. We have a statement that says x is irrational. So statement 6 contradicts statement 1. So we write the words, "We have reached a contradiction," and we say very clearly what the contradiction is. And so that tells us that our assumption that we made earlier was incorrect. Our assumption in step 2 was that XR is rational. So that assumption must be wrong. So we're ready to wrap this up. Since our assumption in step 2 must be wrong, in step 2 we said that XR was rational, and so that since that was wrong, it must be that XR is irrational. So this blue statement is our final statement in its statement 8. Let's zoom out a bit. You see that there is our blue structure of a proof by generalizing from generic particular element, and then sitting inside of it is this sequence of steps that use the contradiction rule. Assume that XR is rational. In other words, assume that the predicate is false. Show that you reach a contradiction, and so therefore you're able to say, actually, the predicate is true. So that's our first example of a proof using the method of contradiction. And I want to stress how important it is to be clear to the reader what you're doing. Be clear when you set up the assumption. It should be in step 2. And be clear when you reach a contradiction, that you tell the reader and yourself what it is that contradicts what. And then what conclusion what you draw from that. You realize that your assumption must be wrong. And then in the end, you say, okay, what's true? What's the thing that's true then? What's true is the predicate. The original predicate is the thing that's true. That's the end of that example. Let's do one more example. Prove this. If A and B are rational, and B is not 0, and X is irrational, then A plus BX is irrational. Notice that this is a universal conditional statement. So I've written this big universal conditional statement as just simply a universal statement. So it's actually simpler to do it this way rather than to try to keep the if-then form in a formal statement. Notice that Q star means non-zero rational numbers. Okay, so let's prove this using the method of generalizing from generic particular elements and this contradiction rule. So there's our first statement, which we have no choice about. That's the beginning frame of the proof by the method of generalizing from the generic particular element. Now we know how this proof is going to have to end. It's going to have to end with that statement. Now we'll go down and put that on the next page. So we know that our last statement is going to have to be that a plus bx is irrational. So let's zoom out and see that frame. There's the first statement that we had to have there because it contains all the stuff mentioned in the domains. And then there's the last statement that we had to have there because it mentions what's in the predicate. Now we know what else is going to have to be there in a proof by contradiction. We know what the second step is going to be. The second step is going to be that we assume that the predicate is false. And that's an assumption. All right, where do we go from here? Well, notice that we have a defined expression. A is rational, so we have to follow that up by unpacking that. We have another defined expression. B is in Q star. That means B is a non-zero rational, so we have to write what that really means. So we have no choice about this fourth statement. It's got to be there because of that. Now look, what else we've got? We've got this statement. A plus bx is rational. That's a defined term. So we have to follow that up with a statement unpacking that. To say that a plus bx is rational means the following. Let's combine stuff. We have three equations written down. We have this equation, we have this red equation, and we have this green equation. Let's substitute the equations from 3 and 4 into the equation for 5. So we substituted 3 and 4 into 5. Now let's do some arithmetic. So look what we arrive at. We arrive at this equation. In that equation, the numerator is an integer, the denominator is an integer, and the denominator is non-zero because k, m, and q are non-zero. So that tells us that x is rational. But wait a second. Earlier in the proof, we have a statement that says x is irrational. X is irrational was in statement 1. So this statement that we just wrote, statement 8, contradicts statement 1. So this is where we wrap up our proof. So statement 8 contradicts 1, so let's say more. So our assumption was wrong. So our assumption was wrong. It's important, I think, very important to say that kind of thing, to tell the reader what they're supposed to make of this. We've reached a contradiction, so what does that tell us? Our assumption was wrong. Well, what was our assumption? Our assumption was here in statement 2. That's the only thing in the whole proof that wasn't completely justified. Everything else we did was justified. That's the only thing that could possibly be wrong. So that's the assumption is the thing that must be wrong. And you want to be even clearer than that. So your assumption was wrong, then what's right? Well, the assumption said that a plus bx is rational. That's the thing that's wrong, so the conclusion is a plus bx is irrational. There's our proof by contradiction. So let's zoom out and again look at the structure. You see that there is the frame of a proof by method of generalizing from generic particular. Started with statement 1, which was the statement of all the things mentioned in the domain description, and we ended with this statement that was the statement of the thing that was the predicate. Oh, and that should be statement 10. And then within that we have this frame that's the frame that uses the rule of contradiction. We assume the predicate is not true. That's the assumption. We reach a contradiction. In statement 9, we point out that we've reached a contradiction, and so therefore the predicate must be true. Now, I want to discuss examples where a proof by contradiction is unnecessary. So this is maybe the most important thing of this video, that contradiction proofs are overused. So I mentioned when we did example 1 that's an example that the book wants you to prove using the method of contradiction. Remember how a contradiction proof goes. We have to assume that the statement is false. So that is, assume that there is a least positive rational number. So we could call that number R. At the end, we have to reach some contradiction. And from that, we conclude that our assumption was wrong, the original statement was true. And that'll be the end of the proof. That's the structure of a proof by contradiction. Well, what's the contradiction going to be, and what's the middle of the proof going to be? Well, the idea is, let's go back up and look at example 1. Example 1 was to prove that there is no least positive integer, and we did this proof that consisted of these 4 steps. Suppose that R is a positive rational number. We showed that there exists a Q that's smaller. These steps here are the steps that we need to bring down and put in our proof down below. Now I'll do that, and then I won't make you wait while I slide this thing all the way down. I'll just put it there, and then we'll scroll down and find it. So I've taken those 3 steps and I've moved them down and I've put them inside that proof that we were working on before. There's our proof. There's the frame that we had, the assumption that the statement was false, and then we have to reach some contradiction. Well, how are we going to reach that contradiction? In statement 1, we have a positive rational number called R. Now we can use these steps from example 1 earlier in the video. So these steps, I'm going to move them up a little bit. These steps started with knowing that there's some positive rational number R, and the result of those 4 steps was they showed that there exists a positive rational number Q such that Q is less than R. So what do we make of that? Well, in other words, if we found a positive rational number Q that's less than R, that means that R is not the least positive rational number. Hey, wait a second. That statement contradicts what we said up here. We said that r was the least positive rational number. So we're ready to wrap this up. We've reached a contradiction. You want to tell the reader very clearly what contradicts what. Statement 5 contradicts 1. And then tell the reader what you're supposed to make of that. Well, that means that, therefore, our assumption was wrong. Our assumption was up here. So if our assumption was wrong, it means that the original statement can't be false. It must be true. Now, if you find this all confusing, that's the whole point of what I'm doing here. The thing is, this is the kind of thing that gets proved using contradiction all the time. And it's confusing. And it's crazy because you can see that we had a proof, the very first proof of the video, that was a 4-line proof, and it worked wonderfully. And this proof by contradiction takes that short proof and bundles it with this frame that's the contradiction proof frame, which just makes everything harder and more confusing. So this is a perfect example of a proof that's done using the method of contradiction that would be far shorter and far clearer if it was just done as a direct proof. I'm going to set up another one of these, but I'm not actually going to do it. We're going to revisit example 2. Prove that for every integer n, 3n plus 2 is not divisible by 3. Well, the proof structure would be to prove by contradiction. Basically, you assume that 3n plus 2 is divisible by 3. And then you would work to reach some contradiction and conclude that therefore 3n plus 2 must not be divisible by 3. And that would be the end of the proof. But the thing is, these steps are longer than the steps that we used to prove example 2 without the method of contradiction. So you see that using the method of contradiction adds this layer of confusion because you have to assume something which you know doesn't seem right. So you have to spend all this time working with this thing that doesn't seem right, and then you reach some contradiction and you have to undo the assumption, and it's confusing to do a proof by contradiction. And you end up with something that's longer and more confusing when we had a short proof of example 2 earlier that did not use the method of contradiction. The very last example that I'm going to do of this sort, example 3, prove this statement S. Prove that if n squared is odd, then n is odd, using contradiction. So we would start by saying, suppose that n is an integer and n squared is odd. And we would have to end by saying that n is odd. And that would be the end. So the way that this would go by contradiction would be that you would suppose that that q of x is not true. You would assume that n is not odd. Now where would you go from there? Assuming that n is not odd, you'd have steps like we did in example 3. So we would show that n squared is not odd. And then you'd have to say, oh, wait a second. That contradicts that. We have n squared is odd. Earlier we had n squared is not odd. So we've reached a contradiction. So our assumption was wrong. All right, so what do you do with that? Well, if our assumption was wrong, what was our assumption? Our assumption was that n was not odd. So if our assumption was wrong, that means that n is odd. Okay, so finally we proved that n is odd. But look how confusing this is. And also, look what's in the middle of it. In the middle of it is the proof that if n is not odd, then n squared is not odd. That thing in the middle, that red core of the proof, is the proof of the contrapositive. Well, those red steps are all we need to prove this. That's a universal conditional statement. These red steps are a proof of the contrapositive, which is the same thing. We're done. If we can do those red steps, we don't need anything else. So to turn this into a proof by contradiction means that you add all this junk at the beginning and all this junk at the end. You add this frame that's the frame of a contradiction proof, and it just adds confusion. It's far better for something like this to prove the contrapositive and leave it at that, not try to turn this into a contradiction proof. It ends up being, as a result, it would be the proof of the contrapositive wrapped in that confusing frame. All right, let's wrap this up. So the proof by the method of contradiction is confusing, both for the writer and for the reader, and for that reason it's always best to avoid it, if possible. And in many situations, a universal statement of this form can be proven using just the method of generalizing from the generic particular. And in those situations, it's definitely best to avoid proving by contradiction. All right, sorry this video has been so long, but that's the end. Thank you. Bye.